Hello and welcome to the 5th Long Products webinar. I am Ken Landau, staff engineer at AIST. This webinar will feature the achieving the limit of interbillet time to increase bar mill production. As with all AIST functions, we must go through the antitrust compliance guidelines first, which are listed on the screen. Do not discuss with others your own or competitors' pricing procedures, or anything that might affect pricing, such as costs, discounts, terms of sale, or profit margins, or anticipated wage rates. Do not make statements about your own prices or those of your competitors, and do not talk about what individual companies plan to do in particular markets with particular customers. Anti-harassment policy is shown. It'd be kind of tough to harass on this format, so there it is. Please follow it. Things to know. We have disabled the attendee audio, but we do welcome questions to the presenter. And we ask that you do that through the Q&A feature, and that way it will stay with these recordings. The Q&A is down at the bottom, typically at the bottom of your screen if you put your mouse down there. And again, that helps us track the questions and answers. The host and moderator will determine which questions are presented to the presenter. The session is being recorded and will be available on-demand replay on AIST's website. If you do have any technical difficulties, you can contact training@aist.org. Another important reminder is photos or recordings of the presentations is strictly prohibited. You'll be given a link to access the presenter contact information and recordings following the end of the webinar. And with this webinar, it couldn't happen without our sponsorship from Nidec Industrial Solutions. They offer products, turnkey products, and services to industries where power conversion is critical. Nidec's Avtron encoders brand of bearingless magnetic encoders are designed to survive applications in high temperature and high humidity environments, and are built in their plant in Cleveland, Ohio. Zaldo, founded in 1853 and acquired it by Nidec in 2012, has been manufacturing motors since their invention. Today, factories in Mexico, the United States, and Italy build motors of all types and sizes, including AC induction, DC mill motors, and large specialty motors. Plus, they provide motor rebuilds. Need to replace your rotor in your multi-megawatt mill motors? Nidec can engineer a solution. To their long history in motors, they have also been making MV and LV variable frequency drives since their invention, and have a full lineup of those drives plus DC drives and load commutated inverters. Finally, Nidec's expertise in power conversion is put to work in their power quality solutions to correct common problems in steel mills, including distortion, power factor, and arc furnace flicker. All these solutions are available with automation and controls. In fact, Nidec controls have been installed in over 1,000 metal making mills worldwide, and over 280 of them being in long products mills. So thank you, Nidec, for sponsoring this. And let me introduce our moderator, Chris Petrie. He's a roll shop supervisor with Steel Dynamics, their structural and rail division. With that, Chris, I'll hand it off to you.
All right, I'm gonna quickly introduce here our presenters today. There's also some other people I think that are going to be helping with the question and answer that I don't have a lot of information on, but they will be involved in answering your questions as we move along. First here I have Francesco Scarlassara. He's an electrical engineer with Nidec Industrial Solutions, specializing in automation controls development and standardization for metal production. He began his career as a rolling mill commissioning engineer with Ansaldo Sistemi Industriali in 1992. In 2003, he was promoted to the R&D department to develop mill automation and steel product tracking solutions. His experience also includes copper mill automation from melting all the way to the coiling process, large photovoltaic plant power control and grid interfacing, embedded system firmware development, low voltage drives, and IT infrastructure design. He now specializes in root cause analysis, troubleshooting, and production improvement. He also assists commissioning teams for plant automation, fine-tuning, and Industry 4.0 implementation. Joining him today will be Bill Merkel. He is the manager of product development with Nidec Industrial Solutions. He began working with Nidec in 2011 as manager of product development. He is responsible for the management of North American drives and systems sales channels, project estimation, and new product development programs. He previously managed the U.S. project engineering and field service functions. He has had more than 20 years of experience in electrical engineering, global product management, business development, and business unit management in the instrumentation, automation, and power industries. Mr. Merkel holds a bachelor's degree in electrical engineering from Youngstown State University. So at that, I believe, Bill, you're going to take off with that?
That's the plan, Chris. Thank you for that kind introduction. Let me see if I can get the right screen up here. And can you tell me if you're seeing the slide, please?
You're good.
Okay, and all right, I'm not sure what's going on, but we'll deal with that. Okay. My software is complaining. Hang on 1 second. Stop sharing and play. There we go. Some interaction between the two platforms here didn't go well. And share screen, and it should be back. Is it back?
Not yet. There you go.
Okay.
It's loading. All set.
All right. Thank you. Thank you again, Chris. A little more background on Nidec. We're the largest motor company you've never heard of, probably. Our company was built by Mr. Nagamori, shown there in the picture. And he started the company in the hard disk drive and precision motor areas. Back in 1973, literally him and 3 guys in a garage in Kyoto, Japan. Today, we have over 140,000 employees and a $50 billion market capitalization. A lot of that was done through an aggressive acquisition strategy that Mr. Nagamori put in place over a decade ago. And that's why the old names you may have heard of in the past, Ansaldo and Avtron and parts of Control Techniques, were acquired by Nidec and integrated into the Nidec Industrial Solutions Group, which is part of the green area down there in the lower left. So we're about a $500 million part of the Nidec family. That's who we are. We do have deep expertise in automation and controls of steel mills, and that's at all levels. We have been installed in over 1,000 metal making mills and over 280 of them being long product mills. Our presentation today is focusing on interbillet time. That's largely a level 1 automation effort involving PLCs and sensors. And we'll share our experience in this, which goes back to the 1980s and includes wire, bar, rod, rebar, and profile mills. A long product mill has 3 primary performance indicators that drive the profitability, I guess I'll say. Yield, utilization, and billets between cobble. Yield is the measurement of production loss from furnace charge to finished product, determined by weight. And utilization is actual production time, rolling time, versus total production time available. Interbillet, time between billet between cobble rate is critical because cobbles have a significant impact on both the yield and the utilization. It impacts yield because of the scrap it creates, reducing the tonnage, and it impacts utilization because of the downtime it creates. Often the best way to increase utilization is to reduce interbillet time. But that trade-off at some point causes increases in cobbles. And since cobbles create scrap and reduce utilization, that has a big negative effect on production. The chart illustrates this idea on the left, on the right. Rolled billets per hour increase from left to right as interbillet time reduces. Up until a point shown by the effective blue line where production falls off the cliff. In red, we show an example mill where their variation in interbillet time is 4 seconds, illustrated by the difference between the 2 balls at the end of the red line. And in order to avoid cobbling and the crash in roll billets, this mill is operating at a 6-second target interbillet time. In green, we show how if we can reduce that variation, the mill could run at 3 seconds or less if you can get variation or that interbillet variation time down under 1 second. So the challenge is to operate at the sweet spot of the smallest interbillet time that delivers the highest production rate. And to do that, variation is our enemy. We need to remove that. So how to reduce that variation and reduce that target to operate in the sweet spot is what we're going to cover today. Have to take a comprehensive view of this when you look at a project to operate in the sweet spot. Of course, the mill is made of lots of mechanical equipment that has its own tolerances of operation. And the primary area of concern for interbillet control, the rolling and shear areas. Sorry, hold one moment. Are normally the rolling and shearing areas. But even the cooling bed and discharge funds of a mill can introduce limits to interbillet improvement. So we need to consider the whole mill's potential bottlenecks when we're looking at reducing that time. Electrical equipment like the blue motors and the drives, control stands, may have power limits that also determine the achievable rate of production. And the control system, including the sensors, may have a big role in determining the repeatability and accuracy of the rolling and shearing functions that we need to focus on. So your automation team must understand and integrate the capabilities of all these areas to achieve an interbillet improvement project. To do that takes a plan. And here's a simple checklist for doing that. It's pretty straightforward. Normally, we find that the mechanical limits production equipment are known by a mill, and that interbillet time is not limited by the capability of the mill itself. Likewise, we find that mills normally have good understanding of the electrical power distribution in their mill and the capability of the drives and motors. And normally, that is not so much of a concern for an interbillet project. If there's any question in these two areas, the mechanical or the electrical power, then we recommend that you engage a consultant who can be brought in to do an analysis of the capability of the mill. And if a survey is needed, it's important to perform that with your team that will be doing the automation and controls work. Working together, they can understand the mechanical and electrical issues and ensure that the control experts inform the control system upgrade with that information. So because the mechanical and electrical systems don't normally limit interbillet time, our focus today is going to be on the sensors and field devices and the rolling and shearing controls in the mill. So here we need to do a careful study along with an understanding of best practices in mill control to achieve that high repeatability, that low variation of time between billet, and then reduce that time to the sweet spot. Finally, once you've understand how you're going to do that, you've got your project costs understood, you should have your production increase targeted, you're ready to roll together a project justification for management, and hopefully move forward with a good performance improvement project. With that, I'll turn it over to Francesco, who's going to dive into more technical details here. Francesco?
Hello, everybody. Thank you, Bill. Well, we first need to confirm the electrical power system. And the most interesting item in the electrical power survey concerns the motor operating at or close to the constant power zone. Normally, the mill operator will reduce spare part requirement by using the same motor in the roughing mill and also on the finishing mill, with the motor running faster in the finishing mill than the roughing mill, of course. This means the finishing mill motors are operating nearer the constant power range, even considering gearboxes that matches the speed requirement to the motor design speed. Many mills are concerned that rolling speed cannot be increased because drives that are operating a motor in the constant power zone will or could trip to protect the motor armature from overvoltage due to the sudden speed change. With the proper control of tension and the reduction of speed variation, the motor is able to safely operate at higher speed in the constant power zone without tripping the drive due to overvoltage on armature. This is very important. So the full motor rating range, both power and speed, is always available. You should not be afraid to run the line faster or be afraid to run motor into the constant power zone with a well-engineered control system. A well-engineered control system can achieve a speed variation below 1% and also permit a higher rolling speed. Later, we will explain how to achieve this level of control. Every modern mill uses a cascade control system. The cascade control system sets the target input speed of each stand. based on the stand's area reduction. This is known as R factor. R factor is simply the ratio of the area going into the stand divided by the area going out of the stand. It is also the same as the ratio of output to input speed, of course, provided that there is no tension among stands. For each stand, the cascade control then applies the stand's target R factor and converts the material speed into angular speed. The drive then uses the encoder feedback to maintain the angular speed target provided by the control system. We have two other feedback loops that are used to achieve consistency by controlling the tension on the product. The consistency is done in the rafting mill by the minimum tension control and in the finishing mill by the loop control. These feedback loops achieve their regulation by adjusting the speed of the upstream stand. In the most of cases, we care about those now. The cascade control constantly adjusts the target speed of the stands based on information it receives from the tension loop and controls to keep the mill synchronized. The problem with this scheme, as normally implemented, is that it cannot control for variation between billets and for mill wear. For example, interbillet distance, maybe slight differences in billet dimensions, billet temperature, roll wear, and so on. To improve the mill production speed, all these variations must be controlled. So, the control survey will focus on the PLC and the sensor for the rolling and shearing function. The image that you see shows the primary sensor of interest and indicates how to assess each sensor for a successful control system upgrade. And now we will try to review each sensor. So first we have drive torque feedback. And from our point of view, any drive can be used because a successful implementation can even be achieved with analog drive. For example, torque control can be managed with the current feedback on DC motor. Of course, modern drive perform with a higher responsiveness and better signal integrity, but also old analog drive can do the job. We also have a very important sensor, that is the loop scanner. If you want optimal control, you require real-time signal of position, of the bar position, with time resolution of 10 milliseconds to 20 milliseconds maximum. Normally, loop scanners support this rate of feedback. It is important, of course, to confirm this capability is present in the looper. For what concerns motor encoder, normally an encoder with 1,000 pulses per revolution or higher is sufficient for optimal control. And if the drive is operating correctly with encoder, then a good control system can achieve a proper material cut. A special encoder or additional encoder is not required. For what concerns the HMDs, we have an opportunity here. The opportunity is to simplify the control system and improve the uptime. The goal here is to use the minimum number of HMDs on the mill. A well-implemented control system can achieve an optimal interbillet time only with an entry HMD, an HMD for each shear, and a final exit HMD. Some mills of all design have HMDs between every stand. These HMD can be removed, and this may increase the utilization of the mill because this sensor can be a source of downtime. Just think about misalignment, dirt, and other situations. In some cases, even the HMD for the first shear might not be required. additional shear do require an HMD. You know, the first shear, on the first shear, roughing shear, normally the material speed is lower, and we can achieve a proper material detection using information coming from the stand, and we can also afford to take out an HMD even there. For what concern the impact sensor, the shear impact sensor, is used to synchronize the incremental encoder signal to the knife position. Some mills use an additional encoder for detecting the knife position. Either can be used. Signals are interlocked with the automation system so that the shear does not cut in the middle of the billet or other incorrect time. And now, shearing control. Shearing control is accomplished with a PLC and does not require any special card for IO computation. The positioning and speed loop can be implemented completely inside the PLC. When the PLC is programmed in order to provide a torque reference to the drive, then any drive can be used on the mill because we are using the torque reference to the drive. And of course, there is a kind of legend in the industry that says that the speed control of a shear must be done inside the drive or using some special hardware due to the dynamics of the control. This was true when the PLC has less computational power that is available within the 10 or 15 years. Part of the survey will be to determine the age and capability of the existing PLC to ensure that the speed control can be performed inside the PLC. Keeping all the control in the PLC also allows for better control through feed-forward control and also tighter integration with the entire control system. Just think all the systems, share control and mill control cascade are running in the same PLC. The control communication bus is, of course, equally important. Here we must have a deterministic bus with high speed. And any modern PLC using Profinet, Profibus, or Ethernet IP is capable to do the job. Okay. If we want to achieve a speed variation below 1%, then the manual adjustment of R factor by an operator must be eliminated because that is a primary source of variation. We must reduce relative variation in speed between stands so that the system is as stable as possible. When the system is stable, the interbillet time variation is stable and the mill can operate closer to the sweet spot. The table you see shows the foundation of the adaptive control necessary to eliminate the manual adjustment and reduce relative variation in speed. As you can see, we always focus on reducing the manual intervention from the operator. The primary sensors are shown for each column. Primary controls are indicated in each row. At the intersection, we show the effect that the control of function can have on reducing variation. For example, in addition being the main feedback for tension control, variation drive torque is the most critical for adjusting tension control to adapt to changes in material temperature. Drive torque variation can also be used to compensate for material impact to reduce variation in lead speed. We have to notice that the drive torque is a primary sensor because a variation in torque is used to do the most of the critical adjustment. And the good news is that it's free. You don't need additional sensor or whatever. It comes from the drive. And as we stated previously, most existing drives are capable of providing torque feedback. Even if we are using old analog drive, it's possible also to use the current feedback to elaborate the torque feedback. The controls must be programmed to adjust what happens on the next billet based on the information from the previous billet. In the end, automation just controls the following. First, the stand speed reference for tension control, loop control, and impact drop compensation. Second, shear knife speed and synchronization. Finally, this is very important, short billet prevention. We have to prevent the billet to enter on first stand with less than, say, 1 second between billets. This self-adapting mirror regulator will adjust speed reference on stand and will preempt the adjusted speed on the following billets. This will reduce speed variation to a minimum and produce optimum material size from the beginning of each billet. This process will automatically adjust for billet temperature and the roll wear, and also for slight differences among billets. That is a very common situation, where the billets are not all of the exact same size. We have to deal with that. Shear will just adapt to actual material speed using stand motor encoders. The shear will take the speed feedback from the stand motor encoder. When all this is implemented, the operator does not set up a conservative R factor to avoid cobbling by looking at torque graph. You don't have to set tension between stand just to be sure to avoid cobble. And when you start up the mill, the operator just can set up a conservative speed, and then the adaptive control will bring the mill speed to the sweet spot. Further, operators are not required to constantly monitor the stand drive torque and manually adjust the motor speed to adjust R factor. These adjustments are made automatically and adaptively to reduce variation and maintain operation in the sweet spot. So, as you can see, we always focus on reducing operator intervention. To do all this, you must have an automation tool that can implement the adaptive control in the scheduled maintenance shutdown. For example, you can make it during a reheating furnace maintenance outage or also on a longer holiday outage. The automation team must have a clear plan to replace only the critical function blocks and libraries. And they will preserve as much logic as possible. For example, if you have the logic that runs all the lubrication units and auxiliary equipment, then you can keep that logic. If it is needed, they can also replace other control equipment, such as control desk that are worn out and need to be replaced. Our experience is that good automation team will have to pre-test the adaptive function. This should be done with a simulation of field I/O changes to confirm the operation of the control system with the common variation that will occur in normal operation. In this way, the complete mill operation can be tested prior to the outage. You have also to put a test control system in operation. Of course, the team must also prepare for replacement of I/O and validate correct connection to a new adaptive control system, prepare the network, computers, and potentially change the control system of the drive if you want to upgrade them, for example, from analog to digital control. During the commissioning, the team should enable one regulator at a time. For each regulator, test for a few billets or a few hours. Improving the conservative default setup, you can achieve better control and speed a kind of fine tuning. So the regulator should have some default value that are pre-tested and able to achieve a good result in a short time. Of course, the process of achieving sweet spot operation can take days or weeks, depending on the result of the test. But this is important, the production will still match or exceed the historical production immediately, because you are deploying a well-tested system.
Thank you, Francesco. Often, Interbillet improvement project can be surprisingly affordable and have surprisingly good fast payback. To develop the estimate you see here on the left, we used a bar mill we're very familiar with because we've done upgrades there. And our premise is that the mill, like we mentioned earlier, is using in-house resources and expertise, and will implement the adaptive control method Francesco just described in slide 14. We assume there's no need for mechanical changes and the power system changes or the drive lineup. And the left shows that we budgeted $10,000 for consultant surveys. And we budgeted about $230,000 for the internal team, cost of labor and PLC acquisition, maybe new cabinets and I/O to do the project in-house, including reprogramming of the rolling and shearing feedback for that adaptive control. In the table on the right, you see an analysis of potential revenue increase. We assumed a $5.95 per ton rebar price, which is not a pricing problem because we just got that off of Google. It's common information of what folks in the industry say is a sort of a common market price right now. And with the assumptions on mill utilization, an improvement of 2 seconds in interbillet time, yielding 2.4 billets per an hour. So we get so many additional billets per year, and at 2 tons per billet, we get so many more tons per year. What Google says the price per ton is, yields a revenue of 18.5 million per year additional revenue. Because most of the gross profit for this increase in revenue flows down the profit and loss statement down to the bottom line, not quite all of it, but marginal increase in production like this normally benefits the bottom line by most of the gross margin percentage. This project could pay off in as little as 3 months, the assumptions that we've made here. Assuming again, as Francesco stated, that this is done during a normal mill outage, implement the project. Here's a short case study, an example of a successful project. In this case, the mill was able to improve production by about 6 tons per hour. And if you remember the earlier graph of the sweet spot, we actually took our red section of the graph here from this example. They were operating with about 4-second interbillet time variation, and they had set their target to 6 seconds to avoid the cobbling. After we improved the control system for rolling mill tracking with the aspects we show here, they dropped their average interbillet time down to 3 seconds. That became their target. And the interbillet variation dropped down to a little bit less than a second. So they were able to improve their interbillet time from 6 to 3 seconds overall, lining up with the example we just gave in the last slide. That concludes our presentation. We want to thank everybody for your attention. encourage you to improve your mill performance with an adaptive control upgrade. Our emails are shown there, so you can shoot us questions after the seminar. Now we'll take some questions from the attendees.
See a question regarding how the billet between cobble is measured by mass or time. Well, we measure by time. Of course, the cobble also causes material loss, that is for sure. But the most important is the time you lose in order to clear up the cobble. And it depends on your organization, how you're set up, and the product you're rolling, and where it cobbles. If it cobbles on the rafting, it could take maybe 20 minutes or half hour in order to clean up. If it cobbles other area, of course, it's easier. But the important is to be able to run with a short interbillet and do the best to avoid the cobbles. So we should always focus into avoiding interbillet below a certain threshold that is normally about 2 seconds. And run, of course, with the interbillet closer to the sweet spot.
The next question, Francesco, is can we name the mill where those improvements were realized, or is that confidential? And we don't have the permission from the mill owner to release that information, so we will have to keep this confidential. The next question, Francesco, is there any metallurgical effect on the products that have been studied? And if yes, how are the effects on the product quality?
The effect on the product quality by what kind of a situation?
I suspect they mean by decreasing the billet, the BBC, the billet between the interbillet time. Is there
any metallurgical?
Yeah, because you discharge from the furnace faster, right?
Well, of course, the furnace must be able to keep up with increased production, and but from the rolling point of view, that the metallurgical results should be better, because if you run at a stable speed and a faster speed, all the temperatures on the roll and all the mechanical equipment will be running at a stable temperature. So always normally also the product size, the material size you produce is better if you're running with a stable situation. Of course, running faster put additional burden on the furnace. When you run faster, it could be that the billet output temperature drops. And if this happens and you're not able to prevent this by adjusting the furnace, then here comes into play the role of the adaptive control system. The adaptive control system is able to adjust for different billet temperatures, because when the billet temperature are different, all the metallurgical phenomena are changed, and the tension between stands is different from what you expect. So the adaptive control must be able to adapt to the changing billet temperature. And of course, you could have some situation where that depending on the type of furnace, also the billet temperature is not the same along the billet. If you have a pusher furnace, then you have 2 or 3 spots on the billet where the temperature is lower. And where you're rolling faster, you might also see that the billet is darker in 1 or 2 spots. Then the adaptive control system must be able to deal with this. I don't know if I answer the attendees question, or if you need more explanation about this. We also have a situation where the furnace output pace maybe is not constant. In this situation comes into play a control where you must control that the billet entering the mill are not do not stack together, do not rear end. Because if billet rear end, then you get cobalt. That's for sure. That's guaranteed. So what you must try to achieve is keep the minimum time between billet, minimum interbillet. We put attrition normally at 2 seconds. And this threshold is important for 2 reasons. First, if you run at closer, a shorter interbillet, maybe the loop expeller are not able to raise or lower in time. The shear are not able to perform the head and tail cut within the short interbillet, and you have, for example, on the rafting shear, you need to give up to the head cut of tail cut, and this can produce can create a problem in the following stand. Because, for example, if you run with very short interbillet, you give up to the shear tail cut, then all the debris from the shear enter the guides on the following stands, and this could lead to cobalt. So this should be avoided. So you run with a controlled interbillet. The controlled interbillet is achieved by first, keep the mill speed as constant as possible, and second, by using a speed control system, for example, adapting the mill entry rollerway speed, or by stopping the mill entry rollerway in case the rollerway is not run by inverter, because the mill entry rollerway could be run by inverters on more modern mill. Older mill use just start-stop motors. In that area, it's possible to achieve the interbillet control using inverter or start-stop motor. If the billet, for any reason, come too close and they are entering with the interbillet, you forecast the interbillet below 2 seconds, and you have to stop the mill entry rollaway, because this is the only thing you can do. Of course, a stable mill where the adaptive control stabilize the mill entry speed will facilitate the constant material flow into the mill. Then a lot depends on the furnace. Furnace can have even output. Normal can output billets with a constant pace, but sometimes, for some reason, billets do not come out in time, and when they do, 2 or 3 billets come out in a very close time. So all this must be controlled in order to avoid cobalt. When we avoid cobalt, your billets will pay you out.
Mm-hmm. The next question is: do you recommend? Can you comment on a comparison between hydraulic and pneumatic looper actuators? what do you think is
Well, the loop expeller are work in a very harsh environment. And from my point of view, a system running that environment should be as simple as possible. So not a pneumatic system. Normally, I think air control valve can be good enough, but you have to be sure that you have some air accumulator put close to the valve. If you have long pipes from the accumulator to the valves, then you can have a response time of 1 or 2 seconds. If the loop expeller takes 1 to 2 seconds to rise or to lower, then this is a problem, because an interbillet close to that time will not work. You have to slow down. You have to increase the interbillet, because the loop expeller cannot work within the expected time. Frankly, it's a pity. Just one valve that forces you to slow down the complete rolling pace. So air valves, air-based loop expeller with a closed accumulator system, the pipes as short as possible, we normally do the job. You can have those expeller raised in a half second and drop it within half second is more than enough. And also, if you want to have a finer control on the expeller force, you can also provide a 2-valve system where you have where the expeller goes up with a valve, and then with a second valve you freeze you close the air circuit, and the expeller keep a balancing situation where and is not. So this is a system that is more material friendly, that this helps you to keep the material tension under control, because it's not pushing hard to this maximum. Anyway, it doesn't matter what kind of a expeller you have. Is when you set up a loop control, is important to find out for each loop form which is the sweet spot, the height sweet spot, because depending on the material size and on the size of the loop form, then you achieve a better result when the loop is running at a certain height. And that certain height is where you don't have tension in the material.
Okay, thank you. Another question, Francesco, is can this process be applied also to flat products? And do we have anything coming up?
It can be applied to flat product, but normally flat products are maybe run by 3 stands, something like that, where stands run some flat product or also beam products. Those system, in that system, we don't have loop former. There is tension control. The tension control is we have to control the billet through many passes, because the stand will be running sometimes forward, sometimes reverse. So the same billet will make 3, 5, 7 passes back and forth on the mill stands. In this situation, special tension control is needed, because in this situation you do not need to preempt the speed from the previous billet to the next billet. This is if you do this is a mistake. You can preempt the speed, the speed reference from the previous billet in bar mills. When you deal with beam or flat products, they are run with a reversible stand system, normally 3 stand, we call it 3, or I don't know if it's a better term for this. But in that case, a preempt of speed does not achieve good result, because the difference is in material input speed and the rolling situation you find in every pass depend on all the previous passes. For example, all these stands perform a gap adjustment between every pass. A very slight difference in gap adjustment produces a different result in all the following passes. So a preemptive regulation is not needed in this case, but this is just a special situation.
Mm-hmm. Okay, thank you. Another question, Francesco, is it harder to achieve smaller interbillet time when we are dealing with short billets?
Yes, it's possible. Short billet, okay. If you have a 12-meter billet or something like that, it's easier to have a good, a lot of tonnage in production. But if the billet are shorter, it's still possible to run with a shorter interbillet. And depending on the length, on the mill-end rollaway, you might have 2 or 3 billet waiting there to enter the mill, because if you have a long mill entry rollerway, you cannot, for example, you have one billet entering the mill, and the mill is the bill will get rolled very fast, and you cannot wait for the bill to be rolled in order to call the next bill from furnace. The next bill from furnace must be already there on the rollerway, so also close to the stand. So you need an HMD, of course, there to control the interbillet, and you need to put some cover on the rollerway, because billets waiting there will lose their temperature. The temperature will go down, and you know, you need interbillet. You need the billet to be closer to the stand. The mill must wait out of the furnace, so you must put some cover in order to keep the billet speed, the billet temperature at a acceptable level. Is really possible to achieve a higher result with short interbillet, because of course there are some mills weld the billet between each other, but that cause a lot of problem with the material. The best result when you roll quality billets and close to each other. And of course, try to ensure that the furnace temperature is still the temperature that the billet when the billet enters the stand.
Mm-hmm. Thank you. Another question, Francesco, is are the benefits related in any way to the diameter of the finished product, or they're independent of the product mix?
There are a lot of benefits of proper tension and loop regulation. For example, think about this. When the head enters the first stand is always hot. The tail maybe will enter the first stand 30 seconds later. During this time, the tail of the billet will become colder. If the loop control and tension control are not able to compensate for this change in every billet, then you have a thinner material head and a bigger material on tail. In the tail, we will get overfill situation. If you have overfill situation, this is very normal in many mills, so it means that the tension control is not set correctly, because you must compensate not only for billet temperature change between billets, but also for the natural billet temperature change within the billet. If you are able to control this and apply the right tension on the tail of the billet, then the material dimension will be perfect from the head to the tail. And remember, tail overfill problems can be traced down to incorrect speed, incorrect tension control, or loop scanner, loop control running with the loop height set too low. There's too much tension between stands on the loop area.
Thank you. Another question is, how is the tension control signal acquired at the rafting stands?
The tension control is read directly from the drive. If there is a digital control system, then the torque signal or current signal is acquired automatically through the Profibus or Profinet network. In case of analog drive, then we need analog input. It depends. I always suggest that the customer upgrade their analog drive. But if you don't want to change the drive because maybe they have a lot of spare thyristor or other spare parts, they can still work with the existing drive. And of course, you need analog input to acquire the current or the torque. Then if you don't have a torque signal, the system is easily able to calculate a torque signal based on the stand speed and on the current feedback. It's not a big deal, just easy calculation.
Thank you. Another question, Francesco, is how does this methodology to reduce this technique to reduce the interbillet compare with the inline welding of the billets?
Well, this is a very good question. Thank you for asking this. Welding of billets is not easy to accomplish. First, a welding machine are a very complex machine. If you want the mill to run with a minimum effort, you cannot afford to have a welding machine on the mill. They are very complex. You must perform a lot of maintenance. Also, the maintenance that are required by those machines is not irrelevant. First. Second, when you weld the billets together, the quality on the welding is not the same as in the middle of the billet. Whatever the mechanical OEM manufacturers say is not the same. So if you have a welding machine, normally you're running with construction steel where the quality requirements are not very high. So from my point of view, from my experience, I think that a well set up mill where you can run with a short interbillet will be able to produce a very good result. For example, think to this: you have a chance to buy some cheap lot of billets, but those billets are short, are a 6-meter billet instead of 12-meter billet. Then the welding machine will not be able to weld those billets together. It cannot make the welding so fast to weld a billet every 6 meters. So you acquire a small cheap billets, you just roll them as fast as possible. Do not keep the hassle to run a welding machine. It's a very complex machine, and you will not increase the production from my point of view. Just very few mills are able to increase production with a welding machine, but you need a lot of maintenance, and this means downtime and specialized people. And I would not suggest that. If I were a mill owner, I would not want a welding machine.
Thank you. The last question we have right now is, does this technique require the reed furnace to give a signal for discharging billets if it's about a 2 seconds gap?
Normally, the only signal we connect from automation system to the furnace system is a billet call request.
Mm-hmm.
When there is such a signal, then the furnace will do the operation needed to unload the billet. then the pace of this signal can be adjusted easily in order to get the interbillet we want. For example, it depends on the furnace reaction time. Sometimes you require a billet and the billet comes out after 10 seconds. When you know this, you can adjust in order to give the furnace call billet call signal 10 seconds in advance.
Thank you.
Welcome.
That were all the questions that we had.
Well, thank you very much, Bill and Francesco. It was very informative and we appreciate it very much. And thank you also to Chris for moderating. And thank you to all our attendees. Bring up my last screen here. No, I'm not. Well, and thank you again to our sponsor, Nidec. It was, we appreciate it very much. And with that, we'll conclude this webinar. Thank you again.
Thank you. Bye-bye.
Thank you, everybody. It was a pleasure.
Thank you.
Great.
Bye-bye.
Bye. See you next time.